Hey everybody. So today we're going to talk a little bit about exponential growth versus exponential decay. Let's start with a brief review of what we talked about yesterday, which was arithmetic sequences versus geometric sequences. All right, so let's take a look at this first part. We have an arithmetic sequence here, 1, 4, 7, 10, 13. Now this is going up by a constant amount. It's actually going up by 3, right? That's our rate of change, going up by 3. So that would be linear. If we were to graph that, it would form a line. So here we have a discrete graph where they plotted these points. If I was to connect those, it would form a line. Therefore, it's linear. Here's a linear equation. Here's a situation. They kind of describe what's happening in a story. So this guy's a piggy bank. It's going up by $3 a week. You know, after so many weeks, it has X number of dollars in it, right? So the rate of change is 3, right? So there you go. Pretty straightforward. Here's a geometric sequence. Let's take a look at this. It goes up by 1. It goes up by 2. It goes up by 4, it goes up by 8. So the amount it's going up by is doubling. It's not a constant rate of change. It's geometric, right? And if you were to plot these points, if you were to connect these, it's going to create what's called an exponential curve, okay? Because the amount it's going up by is doubling each turn, which is right here. All right, so, and you'll notice it's exponential because the variable is in the exponent. So here we go. They give us a situation where somebody's money is doubling each month. Don't trust that. If somebody tells you they can double your money each month reliably, that is a Ponzi scheme, more than likely. So yeah, and that's a situation that describes it. All right, let's take a look at these. Now these are kind of interesting. This is going to ask us to identify these as either being linear / arithmetic or non-linear / geometric. The reason they don't say exponential is because it doesn't have to be exponential to be considered nonlinear. You'll see why once we get to number 3. So number 1, a car was purchased for $18,000. The car depreciated by 20% each year. So what's happening is we're taking 20% off of the value of the car each successive year. So in this first year, it's $18,000, right? If we take 20% of that, that would be $3,600. And then the next year, let's just figure that out. So 20% of that, we're going to take 18,000. We're going to multiply it by 20% as a decimal, which is 0.20, right? And that would give us 3,600. So we're going to take that away from this, and that would leave us with 14,400. Okay, after the first year. Then the second year, we're going to take 20% of that. So 0.20 times that, and that's going to be what, 2,880. And that's how much was depreciated at that point. So it lost that much value, then this much value. So it's actually losing less and less and less each year because the amount we're taking 20% of is smaller and smaller and smaller. So this is actually considered a exponential decay. So this is nonlinear / geometric. Okay. Here we're earning $9.75 an hour at the new job. Last week you worked 14 hours. So this is a constant rate of change. You're making X number of dollars per hour. That's going to be linear. Okay, so linear / arithmetic. You decide it's time to cut the bad habit of sleeping in. Every time you sleep in past your alarm, you put $1 to wake up early in the kitchen. I think they forgot the jar. In this month, you've slept 23 times. Okay, so here's the thing with this one. There's going to be $23 in the jar for the first month. But after the second month, we don't know if we're going to add another $23 or not. We don't know how many times we're going to sleep in. So, the first month we get 23. Let's say this is X, this is Y. Sorry, Y. This is Y, this is X. So, after month 1, we have 23, let's say. And then after the month 2, you sleep in another 10 times. So it doesn't go up quite as much. Then you don't sleep in at all. And then you only sleep in 1 time. So it's not linear, but it's not necessarily exponential, right? So we're going to call that nonlinear geometric. Mainly because the rate of change is not constant. Okay. Number 4. That's definitely not geometric. There we go. You deposit $4,500 into an account that pays 5% interest every year. After 3 years, you have $5,209 in the account. Okay. So this is going to be geometric / nonlinear because the amount it's going up by is different. So 5% of this will be different than 5% of that. So just by knowing that, we know it's going to be nonlinear. Okay. So let's turn the page here. Okay, so we're going to talk about exponential growth and exponential decay. I rewrote this formula because I don't like the formula they wrote. I think it's garbage. So I think this is the better one, in my opinion. This formula is fine, but it's just a simplified version of this. We want to start with this. So, exponential growth is when something's getting bigger, and exponential decay is when something's getting smaller. Okay, so as we look here, the functional value is increasing as x increases, and by functional value I mean the y value. And here in exponential decay, the functional value is decreasing as our x value is increasing. Okay, so it's represented here. So a is going to be our starting value. Okay, this is our rate, and it's expressed as a decimal. So usually when you're given a rate, it's written as a percentage, but when you use it, you're going to use it as a decimal. So for example, 100% would be 0.1. Sorry, not 0.1, 1.00. 5% would be 0.05. So, yeah. Here, this is the amount of time. The arrow. Time, or intervals that go by. All right. So we'll give you an example in a moment. Same thing here. Just that we're subtracting the rate. So I guess we can write both again. So the starting value. This is the rate as a decimal. And this is the time. Okay, so here you can see the table. X is going this way. X is increasing. Y is increasing. Excuse me. And you can see here that it's getting larger by much larger amounts pretty quickly. So, yeah. So here it goes up by 6. Here it goes up by 24. Yeah, 24. Okay. And here it's getting smaller and smaller and smaller. Basically, we're basically dividing by multiplying by a third here essentially. Okay, let's take a look down here. Is this a growth, decay, or neither? So, well, it's definitely getting larger, so it's not a decay, and the amount is changing, so we know it's not neither. It's not linear, so it is a growth. Okay, let's take a look at this one. So y is getting smaller, and let's see, this is half of that, this is half of that, this is half of that. So yeah, this is decay, because it's basically multiplying by a half. Let's take a look at number 3 down here. On the 3rd day of the release of a new movie, 600 people watched the movie at the local theater. After three days, 480 people watched the movie at the local theater. After 6 days. Interesting. Okay, so let's unpack this a little bit here. So we have to figure out how much it's going down by every 3 days. So every 3 days, let's see, the first one we went from 600 to 480. So we lost 120 people over the course of 3 days. And then here, we did 480. Oh, why did I write a divide? Sorry. 480 minus 384. And that is going to be, let's see, borrow the 7, make that 6, borrow that 7. So 96. So it went down by 96. So it went by 120, then went down by 96. So it's going down. It's not going down by a constant amount. So let's get rid of the growth. It's definitely not a growth. Let's see if it's the same ratio. So let's do this. Let's do we'll do the new amount over the previous amount. So 480 over 600, and then 384 over 480, and let's see if that is a common ratio. I'm going to go grab a calculator so you can see that. All right, so let's take a look. So 480 divided by 600, what do we get? We get 0.80, so 80%. So it went down by 20%. Let's try this other one. 384 divided by 480. Yeah, so we're basically decaying by 20% each time. So yep, that is a decay. All right, number 4. At the beginning of the day, a water tank has 400 liters of water. After 2 hours, they have 340. After 4 hours, 280. Okay, so let's see how much it went down by. So it went down by 60, and then went down by 60. So it's a constant rate of change. This is not a growth, it's not a decay, it is neither, because it's actually it's a linear function. Okay. So really it comes down to this. One, check to see if the amount it's changing by is the same. If it's the same amount each time, then you know it's going to be linear. It's not going to be growth or decay. If it's a ratio, it's the same ratio, then it's going to be either growth or decay, depending on if it's getting bigger or smaller. Okay, let's take a look at these. So, yep, that's a growth. As x increases, y is increasing, and it's not a line. It's a curve. Yep, that definitely looks like a growth. Is this a growth or decay? Yeah, it's definitely a decay. Those are pretty straightforward. All right, number 7. A bird sanctuary has an initial population of 512 birds. After 2 years, the population is 768. After 4 years, the population is 1,152. Okay, so it's not a decay. It's going up. Let's see if it's if the amount is constant. So from 512 to 768. So 768 minus 512 is 256. So now let's do the next one. So, and again, it's after 2 years each time, so we can do that. Oh, let me zoom out so you can see this a little better. Sorry. So 1,152 minus 768. Oop, no, let's get rid of that. There you go. So it changed. So it's not constant. Now let's see if it's a common ratio. So we'll do the new over the previous. So let's do 768 over 512. And we'll do 1,152 over 768. Let's see if that gives us the same thing. So 768 divided by 512 is 1.5, and then 1,152 divided by 768, is that 1.5? It is. So that's a growth. Okay. Here, we're going down by 5 each time, so that's neither, because it's a constant rate of change. Number 9, a cell splits at a rate of once per hour. There's one cell to start, then there's 2, then there's 4. So it's splitting, right? We're starting with 1, then 2, then 4, and then 8, and yeah, that is the definition of exponential growth. The population of a town is decreasing at a rate of 3% per year, and 2000 gives us the number. Okay, so it's not a constant rate of change, it's a percentage, it's going down, therefore it is a decay. Not a place you want to live, apparently. Number 11. You deposit $2,900 into an account that has a 3.5% annual interest rate that is compounded monthly up to 2 years. Okay, so again, it's a percentage. It's going up. That is going to be, because annual interest rate, remember, is when you gain money. Interest, you're going to gain money, so that's a growth. Okay. If there is $2,500 in your bank account, you decide you want to save up for a car. You start to deposit $150 a month for 1 year. Okay, so again, the rate of change is constant. It's not changing. The amount's changing total, but the amount you're adding to it is constant. It's always $150. That's going to be neither. Okay? So I hope this helps. I went kind of quickly at the end there just because of time. We're going to run out of time here, so I hope that helps. Please let me know if you guys have any questions. I'm more than happy to answer them. All right, thanks.